Awesome. Welcome, Peter. How you doing?
Hello, I'm fine. How are you, Trevor?
Awesome. Super excited today. I want to talk about get into the operation envelope of compressors because I really believe this is something that will help a lot of technicians out there because even me as in the field, like I didn't always know where the pressures were and what was actually happening. And I'd love to dive into an operation envelope of maybe one of the compressors from Select 8 or something.
Yeah,
We can
yeah,
talk
sure.
about those conditions when we're running outside that operation envelope.
Yep, I will show you the select, what is compressor and component selection software, which is used in Emerson Europe for Copeland products in general.
Yeah, I love
So
this
let's,
software. Like this software it helped me out so much looking through the CO2 compressors.
yeah. So it's really full of information and it will definitely take to everybody some time to learn how to go through it. So let's start somewhere and we can look what is accessible here and what we can find. I think that at the beginning, as for all the softwares, you have these different tabs. You can see some different settings. Mainly, I think very important for everybody will be to set up properly the units. So either SI units or the Imperial units. I will keep for myself the SI units because as I am used to them.
Yeah, please do.
So, and then you need to decide what actually you want to find or what you want to work with. So we have here different tabs for the families, for the product families. So you can work with compressors, either the scroll or semi-hermetic Copeland compressors. And then there are condensing units and there are also components. So you can again choose based on the indoor, outdoor and different families. So it somehow supposes that you are a bit familiar with the Copeland products before you come into this. And if not, it will only take a little bit more time. And there are also components from Alco controls.
That's
So I
awesome.
will go back to the compressor.
Can you find
And
inside this software all the manuals for each of the compressors?
yeah, for each of the product, you will at the end choose, there are different
Okay.
data types and there are also technical data. So this is a basic summary. There are also some calls on the documents which are related to the product you choose.
Oh, fantastic.
Yeah. And actually it's even here on the basic tab. So you can see the online documentation and it will connect you to the website of Emerson where you can find very fruitful and useful information.
Yeah, I love those. Like I've read hundreds and hundreds of those. If you want to be good at troubleshooting compressors, you got to read those. And I'm sure you've read hundreds of them. You probably wrote half of them. So
Probably some of them, yes. And as we are now going to talk about the CO2 recip compressors, well, let's go from the laptop. So we have the refrigerants here from the long list. I chose the R744 and just click OK. And then you can choose if you want to work with a dew point or bubble point, mainly for non or multi-component refrigerants. So here we have only the dew point and the arithmetic mean temperature. And you can choose also for 50 or 60 hertz basic motor selection. And then there are also different voltage options. And then you can choose either you put your requested capacity here and you can, let's say, you want to run 10 kilowatt compressor or you want to find it and it will automatically choose the proper compressor model. And then you have here the operating conditions, so you can put here whatever, or if you are at the beginning, you can choose the basic rating conditions according to EN standard or RE condition. So what I did, I hit the standard empty condition. So this is in SI units -10 on evaporating, and then it's condensing 45, or you can also switch to the pressure. It will give you the rating condition, and then in the combination of the requested capacity and the condition, it gives you the basic choice of the compressor here. Or if you don't want to go by the capacity and you know which model you want to look at, you will choose it from the drop down menu. So that's the basic selection, and you also have here the basic system diagram, so you can see which values are considered in which part of the refrigeration cycle. And then for the basic selection you are done, and you can go to the main part of the screen, where now I can see the selected compressor, and I can go in different tabs and see what is in there. And there is also not only the one compressor model, but there is the full family, and you can see which is, let's say, without any warning sign here. This is a compressor which perfectly works at the set condition, the chosen compressor, the chosen condition, and there are another ones from that family which have some, for example, exclamation mark, and if you go above it, you can see the warning. So this 4MSL compressor at this condition is above the maximum allowable condensing pressure, and it's simply because of the fact that it is LT compressor, it is subcritical compressor here. But if you, for example, choose here the subcritical condition or the low temperature condition, it will change. And now here you can see that you are within the operating envelope in the 4MSL, but the 4MTL transcritical compressor is out of the operating envelope, which is also can be seen here. So this is the operating range where the compressor can work without any issues.
Yeah, and this is the most important thing that everybody needs to understand. And even before I started, when I worked at Emerson, I didn't know really about operation envelopes. And this is what really helped me grow my knowledge by understanding that each compressor has a specific envelope that they're designed to run in, and they're different. It's not you just get one envelope that
Definitely.
works for all the compressors, but they have different ones specifically. And this is why you need to get into a software like this to understand how that compressor is actually running and working. It's not like I just go up and I put my gauges on and I check my volts and my amps. Oh, everything's good. You need to match that to something, and this is one of the things that you would match it to.
Yeah, you are completely right. It was also a kind of new thing for me, because when I joined Emerson after 10 years working in a previous company, which was not the compressor producer, I only chose a compressor model and I checked only the maximum discharge pressure. If it was fine, I used the compressor, or I asked the supplier to check the compressor selection for me, but I really didn't know all these details. And I have to say that it's much better to see the compressor operating point and to check it in the online software, or somehow software which gives you a response, than only to check it in the papers. If you do it in the papers, you are getting into risks that you oversee something, that you miss an important piece of information. But all these selection softwares, they give you very direct feedback on what you are requesting, and you should not be checking only the main operating points, but also the limits which are expected from the system operation. And then you can be completely sure that what the compressor will be working at, it is fine, or it will give you some limits, and you will need to kind of redesign the system, or the control system in your refrigeration cycle and unit.
Yeah, awesome. And this is what I
Right.
really wanted to dive into is this chart here, because I think this is key to understanding and how to recognize a system having an issue. So as everyone can see that we have an operation envelope and there's a couple lines. Why don't you explain what all the lines mean first before we dive into potential things you can catch?
Yep. On the horizontal line, there is the evaporating temperature, or if you want, it can be recalculated to pressures. So it's the suction side of the compressor, the minimum temperature, which can be used as an evaporating temperature with the combination of the compressor and the refrigerant. And then there is also the right vertical line, which is showing you on the axis what is the maximum suction temperature or pressure which can be used, or in the maximum which the compressor can withstand. And then the two other basic lines are the maximum discharge pressure here. So here we can see it's 120 bar. The bottom horizontal line is telling you what is the minimum discharge pressure which is allowed for that compressor.
The massive range.
Yep. So, and then the corners are not sharp, as you can see. There are some cuts. So if we go on this bottom right line, is the kind of minimum ratio between the suction and discharge pressure. And you need to keep this in order to make sure that you have a certain pressure ratio, discharge versus suction. And it also is important for the compressor proper operation and the reliability.
Okay, yeah.
Because if you, yep,
Yeah, no, this is a good point. So as you can see, it's not a total square on there. So now that it's on an angle like that, and like this is trying to tell technicians that if you're running in this zone, so if we look at it, it could be like 5 degrees Celsius and 14. So we're outside that envelope. Now our pressure ratio or compression ratio, that pressure difference is too low. What can result inside the compressor when we have that low pressure ratio?
yeah. So there are various things which the compressor will not like. If you have these too small pressure ratios, or the compressor might experience that the valve plate is not working as it should,
Mm.
because you need always all the discharge leads especially are kept in the position, open position when you have a certain pressure ratio. If you don't have it, it can start fluctuating up and down during one discharge cycle, because
Yeah.
the force of the spring of the reed is pushing down, but you are pushing from the bottom by the pressure of the gas. And if this is not well balanced, and if you start pushing it up and the discharge reed opens, it can happen that it doesn't stay open during the full cycle and it starts flappering.
Yeah.
And it may lead to the breaking of the valve plate.
Yeah.
So this is one of the important things. And another important thing is that if you are in that region, the power input of the compressor is not big enough. It can happen that you will not heat up the refrigerant inside the compressor, and you will not get the discharge superheat,
Mm.
which is needed for the proper operation as well. And it's also related to the oil and refrigerant mixture on the discharge. And it can at the end lead also to a big portion of the refrigerant diluted in the oil. And the oil is coming back again to the compressor with the poor viscosity. So this is another effect which can happen in this area.
So and that is the most important thing because a lot of the times when this is happening as a technician, we're not there in the field. You know, it's happening when you're at home or you're at another job site. And then you get there and then the compressor is either not running, it could be failed. And you really need to understand this, but you don't have the sometimes the compressor's not, you know, if it's not running, you can't really put the gauges on. But if you see this and notice this, and this will happen, especially here in Canada when it's really cold, like today it's not super cold where I'm at,
Mm.
but I know in northern Canada, it's like -30, -40. And if you don't have the right components in play, say maybe head pressure controls that, you know, keep that head pressure up in the low ambience, you may run into this. So these are some of the things that you want to look for or even think of because it's not only that the compressor compression ratio is low, what is causing that? You know, so now you
Mm.
might have to think about a component in the system, a system related issue causing this low compression ratio or pressure ratio. I love
Yeah.
that. I didn't know about the heat. I didn't think about that at all. That now that you have that low compression rate, you don't have that motor heating up because you got no amps really happening, right? You got
Yeah.
no work happening.
Yes, you are right.
Mm.
And if you are here on the very right of the operating map, you have the maximum mass flow here because you are sucking the vapor with high density. And the lower you go with the discharge pressure, the more mass flow you have.
Mm.
So if you go also to the extremes and also with a CO2 at high pressure and the high density refrigerants at the suction, it can also lead to the situation that you have too much mass flow in the compressor, and there are components like, for example, the suction screens, which can break
Mm.
because of the too big mass flow, which is causing too big pressure drop on that component, for example, the suction screen. So I also did see in some extreme conditions that the suction screens were broken because of this effect of too big mass flow in the suction.
Wow. So this is like your maximum evaporator temperature, just way too high. So now you, instead of, because here it says it's about 7 Celsius is the max, and it doesn't say it's
Yeah.
between 5 and 10, but now you're running at, say, a 10 Celsius evaporator. And now that you have this high mass flow coming back, not only does it do the screens, but would this cause force on the bearings and like the drive bearings and cause damage to the bearings as well? Not only the screens?
If you go high with the discharge pressure, then yes, because it can lead either to the motor tripping because of too big amps, or as you said, there are very big loads on the components because of this too big input power. But actually, I would say that the component sizing is somehow imbalanced usually with the maximum motor power. Yes, these corners of the eye loads are very severe to the component loads, but I think that typically if you don't run here for too long, it will happen you more that you will have the maximum current trip or whatever before you break the components inside.
Okay, yeah, no, I totally get that because you have internal protectors. So the inside the compressor, these motor, you're overloading the motor. Are these PTC sensors inside the motors? Or are they internal line brakes? I can't remember.
On recip compressors, it's PTC. Yeah, there
PTCs,
are
right?
PTC sensors which are wired to the terminal plate, and then either you use the compressor internal protector, which gives the signal that the maximum temperature of the winding was overstepped, or you can also read on some other compressors the resistance, and you can check it in the system and
Yeah.
have this compressor trip.
And some of the protections for this, so we're talking about the maximum evaporating temperature and that high mass flow. So on the CO2 system, I'm pretty sure what I see is maximum MOP, so maximum operating pressure settings in the case controllers a lot of the times, in those evaporator case controllers. So it'll limit those electronic valves opening up. And the way they used to do it in the old like HFC systems, they would have like maybe a CPR or a pressure limiting TXL. Is that correct?
Yeah, it's correct. Just probably one thing, one kind of warning is that if you operate the compressor with variable speed, you need to set up also this maximum current protection in the drive.
Yes.
So then if you run this, whatever system you have on the compressor, you need to set up properly the maximum current protection in your drive.
I love that you brought that up because I had this when I was running the lab in Emerson, Canada. We set up a cascade system and I had a contractor come in, put the drive on the compressor, set everything up, all great. I didn't think anything of it. And then about 3 or 4 months later, all of a sudden the compressor failed, and we're like, What happened? It's a brand new compressor, brand new drive. Everything was running fine.
Mm.
And come to find out, the compressor, it was a ZO compressor. Come to find out, the maximum continuous current was like 5.5, I think, amps. And in the drive, it was set for 16 amps. So the
Yeah.
maximum that the drive could run was 16. So what was happening, it was overloading the compressor consistently for a couple months until the windings fail. So I love that you
Yeah.
brought that up.
Yeah. And in this high load region or high evaporating temperatures region, you have very efficient motor cooling. So in some combinations of the operating condition, it can happen that you will not see the motor temperature trips. So as you just said, you will only continuously overload the motor by the extremely high currents without even motor tripping on
Ah,
temperature, because here you have really good cooling of the compressor, but still it cannot run at too high amps.
mm. And that's something good to know. It's not only the temperature that could trip the motor or the compressor, it's also the amp. So you got to really
Yep,
think,
you should be
understand,
doing this, yes.
yeah, understand which one it is and what caused it. Because looking inside the compressor will tell you, especially if it was failed, you can tell if you had a lot of heat overheating, right? So it's good.
Yeah,
That's
yeah. So because then you will probably not have overheating of the winding, but you can have the overheating on the motor pins where the motor power leads are connected to the terminal plate.
oh, that's
So
a
that
good
are
one.
then also critical places in the compressor.
Wow, that is a
Uh,
great tip. I love it. I hope everybody's taking notes because this is key. I love that.
And then if you go from top right to the left, so actually you are at the maximum discharge pressures, but you go down with the suction pressure, you are increasing the pressure ratio. and the pressure difference, of course. As you go to the left like this, typically the discharge temperatures are rising because as you have the higher compression ratios, there is a bigger temperature difference on the discharge of the compressor given by the thermodynamics. You have also what I have just mentioned, you have less and less mass flow going along the motor, so the motor is less cooled. So also the motor is getting hotter. Either this corner, which we typically call maximum discharge pressure corner, or this very left corner, which is highest compression ratio. If you go at the corner or above, you can see the maximum discharge temperature trips or the motor overheating trips.
Mm.
And it depends on very much on the condition and how the motor is balanced towards the maximum pressures and maximum loads.
Yeah, and that's key to understand. This is why checking that discharge temperature is so important, along with getting your pressures and your volts and your amps and putting this all together. Because we are actually detectives out there looking for this information. Because at the end of the day, if that compressor failed, there was a reason why it failed. And we
Yeah.
got to figure out why, because there's just so many compressors that I've seen all the time over the years that just replaced and just one thrown in, and then that one failed again. And I even did it. I even did lots of them over the years because I didn't know the difference. But this is important to understand that when you're running that high compression ratio with lower mass flow happening, that you're going to start to overheat. And that's really because you don't have that cooling coming back, like you said, right?
Yeah. Yes, exactly. So also the motor efficiency in that left areas is lower. So that's why there is even more, let's say, waste heat coming from the motor because it's running out of the typical operating point with the maximum efficiency, which is typically somewhere here close. Because when you design the motor for given displacement, pressure, temperature, operating map, you typically have the highest motor efficiency somewhere close to the high load or a little bit left from the high load. But if you go to the left, the compressor is taking less power from that motor. The efficiency of the motor goes down, and that's why also the motor as such is generating more heat. And in the combination of lower refrigerant mass flow along the motor is heating up even more and more.
And so
So
this
this area is really the most critical for motor overheating typically.
Awesome. And so in this area, this is the top left corner
Top
of the
left.
operation envelope. So in this one, I've seen this a lot before. I'm assuming this is where you would may need like head cooling fans, liquid injection, potentially demand cooling for compressors. Would that be correct?
Yep. That is definitely that area. So whatever you know from the HFC compressors, that was the case. It's not the case for CO2 because until recently there was no compressor with any vapor injection or anything like this. So with today new technologies from Copeland, which is CO2 transcritical scroll, it's
Mhm.
coming to the market, and you have also this beneficial effect of having vapor injection in the compressor, which can cool down your discharge.
Yeah, I'm excited.
But yet from in HFC compressors, it was typically this area where you needed some head cooling or even vapor injection into the compressor
Yeah, and I
to
think
cool down
right
the discharge.
now, what I'm seeing in a lot of CO2 systems, they'll have some sort of liquid injection into the suction line to cool down the motor, depending on how hot that discharge get or the pressures get. So depending on the manufacturer, you want to go check them out to make sure that they're keeping that compressor, or you as a technician, you're keeping that compressor inside this envelope. Because like we're talking about here, if you get above there, it's going to start to overheat that motor, which is super important. And there's I like that you guys have a couple of different lines there. So you have like this
Yep.
pink line as well as this orange line. And do
Yeah,
you
and
want to talk
that
about
that
those a little bit?
I can, sure. This what is shown here in this left top, that are two typical suction conditions in terms of superheat. So The minimum recommended superheat for transcritical operation is 10K, or if you want 18 Fahrenheit, and that is the bigger operating envelope here. So if you keep this recommended superheat, you can go up to -20 on the suction and 98. I can check it later on exactly, but it's something like 98 bar on discharge. But if you are increasing the suction superheat, it also affects the discharge temperature. The more superheat you have in the suction, the more limited you will be here, and this line will move. You will see the discharge temperature trips at lower compression ratios. And for illustration, there is also this orange line, which is showing the operating map if you have 20K suction superheat. So this is the effect of increasing the suction superheat. It's typically better for safe operation of the compressor, but it gives you a limitation on this high compression ratio corners.
Yeah, and I love that. That's what's key about this, because now I'm in the envelope, but depending on the conditions of the system, I may not be able to run in certain section of that envelope that is approved, because you've tested this and you know that if we're
Yeah.
running there with 20K superheat, 36 degrees superheat, that we're going to overheat that motor still. So you got to keep
Yep.
it under that line in this other envelope. And you could have, in one compressor, you could have 1, 2, 3, 4, maybe even envelopes, because I've seen with the variable speed compressor, and I don't know
Yep. I
about
can.
on the CO2 yet, but there is multiple operating envelopes depending on how it's running. Can you show us that?
Yeah, I can show it. So in Copeland software, in Select, the motor or the compressor models for inverter are shown with this INV at the end in nomenclature. For CO2, it's not, because the compressor would be different, but we need to show a different data here.
Yeah.
Let me switch to the same model. So 30 horsepower model with inverter data. So now I can choose here the frequency drive, or the frequency of the drive.
Oh.
I can go up to 70 here, but then at the operating point which I chose before, I am out of the envelope. So this black dashed line is the original one, which was for fixed speed, 50 Hertz. But as I have now the variable speed model with 70 Hertz, it means the maximum operating speed. The left top corner and also the right corner is lower, much lower. So you get simply out of the envelope with increasing the speed. If you go down, you can see how the envelope grows here. So you can go to upper discharge pressures and also to a bigger compression ratio. It's basically because of the size of the motor, which has to give you bigger power at a higher speed. So that's why it's limiting the envelope with the reflection of the nominal horsepower size, and also the influence on the temperatures is there as well. So
Yeah.
you can see now I am on 50 Hertz, the nominal speed, and I have the full operating map here. And that is one reason why we have here now two different envelopes. This is the line which is similar to the previous, what I was showing, 20K suction superheat. But there is one thing: if you connect the motor via the frequency drive, you automatically decrease the maximum efficiency of the motor, because the motor is not anymore seeing the ideal sinusoid. But what the drive is doing, it's cutting the sinusoid. What the motor at the end sees in a shape of teeth, and actually it's not giving you the full network ideal sinusoid, and the efficiency of the motor with frequency drive is a little bit lower than the motor which is alone.
Wow. So that's new to me. And I think I was told this before, but so everybody knows and understand is that just putting the drive on, connecting a drive to compressor, you will reduce operation envelope. Is that correct?
Yeah, that's correct. You run at a little bit lower efficiency and it heats up more the motor, and you cannot get, let's say, compressor input power on the same level as, let's say, solo compressor without the
Yeah.
drive.
Across
And
the line.
it's different from compressor to compressor how
Yep.
much this reduction is. but at least in the
Wow.
software, in our software, you can check it. If I only use the variable speed models and I go from one model to another, I can
Yeah,
also take only the medium temp. So we have only one family.
that's awesome.
You can see in the software what are the different operating maps.
And that is so key to understand. I love this because this is so important when you talk about, especially adding drives. You're going to see more and more drives. I've been seeing it for years, but now it's just you're gonna see it faster and faster because drives can get you to that right suction that you're looking for. You know,
Yeah.
stabilizing your compressor, your racks out, and you're going to see more and more of the drives on there. But you do need to understand that there's still limitations on the envelope, and that's why you need to get into these programs and looking at the different envelopes. I love this.
Yeah, so I definitely recommend to play the softwares from whoever the compressor supplier is. Take the software which they publish, everybody has it, and spend some time in this before you do the installation or you do the design, or even whenever you have some troubleshooting, you need to do some troubleshooting. Spend some time in the software if you are not sure what's actually happening. And if you know it, still I would do the step extra and I would see the software if there is something else, what can the software tell me based on the condition I put it in.
Yeah. I've learned so much here. I love this, Peter. I want to thank you so much for taking the time to walk us through this because I think this is really important for technicians in the field, even engineers and manufacturers to understand this because it's something that we don't do on the day to day. We think, oh, we put a compressor in and it just works. You know, it's the right capacity and it's the right voltage. It's going to work. But there's a lot of characteristics, the conditions that we really need to understand. And I really appreciate you taking the time to do this. How can people find this software as well as get a hold of you or anyone from your team to if they ever need assistance?
The easiest way is to go on the website of Emerson under Climate Technologies group or Commercial and Residential Solutions group, and then you will easily find the link. I can share it after the meeting, so it can be below the video. Beside this, there are a lot of application guidelines and the manuals for all the components, and there are also general guidelines for refrigerants which can also be used to get some basic learnings about the system design and how the components should be used in each of the system, mainly now with the new refrigerants coming.
Yeah.
And it's not only CO2, there are also flammable refrigerants coming, HFO mixtures, and there are a lot of tricks you need to learn before you start working on those systems.
Yeah, I
So
love it. We're definitely going to get into some of those conversations. I really appreciate your time. I've learned so much here. And Peter, I want to thank you so much.
you are very welcome. It was my pleasure, and talk to you soon.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.